So now my cis isomer is also done. So let us open it. This is the electronic energy. This is the Gibbs free energy minus the electronic energy. So this is basically the other contributions. The electronic energy is not copied previous time. This was my electronic energy. And the total free energy is this. Oh, it should be L3 plus M3. And if I want to compare with respect to the gem isomer, then this is this minus the free energy of the gem isomer. Of course, don't forget we have to convert it into kilojoule per mole, and the conversion is 2625.5. Okay. So this is 3.57. So this actually gives you a slightly smaller energy. So RIBP86 actually trans comes lower than the GM1, and sorry, this one is trans, this one should have been cis. So the cis is actually higher than the like more unstable with respect to the GM1, but at least the trans one is actually coming lower than the GM1. So this is nothing but a basic set artifact effect. What we can do is now we can reperform the calculation, and actually we can then see how the results varies with that. So to reperform the calculation, so this gem but, we can write gembut.inp, and this will be BP86 single point. So in place of RIBP86 opt and frequency, what we can just do, we can just calculate the single point energy in a much higher level, def to QZVP, and the geometry we can read it from XYZ file. gembut.xyz. Similarly, I can make it a transbute BP86.inp. So the only thing I need to change is the name of the XYZ file. And similarly, I can make us cis-but I have to just change the name of the file. So I can run now the jmbut.86.out. Remember, quadruple zeta calculation sometimes can be very costly. This is the final single point energy. So I can so this was BP86 def to SVP. So we can run the same job for the trans. There is some problem. It's trans-but. So just from the energy, I can add the vibrational correction, which is calculated from the def to SVP. And then I can calculate the delta GS. This one. So I can take the single point energy, add the free energy contribution, calculate the total energy like by adding the electronic energy at the QZ level and the other correction got from the SVP level, and then I can calculate the. So you can already see that increasing the basis set actually it already changes the sign. So now the sign is consistent with what is the experimental one. Now let us run the cis one. So I will add the electronic energy here for the sys also, like the rest of the contribution for the sys also. And the relative free energy in this case is 5.49. Remember the experiment was more high, so now we need to go to hybrid functional. So we were only working with GGM. Now, at this moment, it is very tempting to use the same input file and replace this gem, this BP86 by the bitrelip, and everything remains same. But I will always advise you to make a new input file, although it's more computationally, it's more of a work, not computationally, but because once you use the same input file, it will overwrite your old number. So if you want to go back and look at the cross check your numbers again, that is no longer possible. So it's always a good idea to create a new input file with a proper name, so that you can always go back and check the numbers. Let's bitrelip. So it's Rij cos x now. Bitrelip. So it's there is some problem. Let us see what is the problem. It's Rij cos x. The bitrelip spelling is wrong. So the gem bitrelip, I can make it a trans bitrelip. And I can also make a cis bitrelip. So we can submit the other jobs also. Generally, it's not a good idea to submit more than one job at a time if you are working only at your laptop, because once it have more than one job, what happens is that it puts a lot of pressure on the laptop's cooling system, and the laptop's memory and hard disk. So we'll avoid this kind of thing. We'll let the job run, and once it is done, then we'll do our analysis.